So my name is Dimitri Solomatine, in Russian Dimitri Solomatine. But when I was getting my first foreign passport, Ministry for Foreign Affairs added E in the end because they were speaking French, and otherwise it would Solomatin would sound, and if you add E, it becomes Solomatine. So that was a tradition, not anymore. So my name changed in Latin transcription. So I have problems traveling sometimes because they say, oh, it's not you, it's a different person. Okay, anyway. And I will speak about hydroinformatics. And accent today would be on optimization, actually. And why this talk is the first one. Perhaps we know in the morning many people are late. So the least interesting talks are put in the morning because then, okay, they wouldn't miss much if they're coming late. So I think that's the reason. I'm from IHE Delft Institute for Water Education, which is in Delft in the Netherlands. It's a postgraduate institute. We are inviting master students and PhD students. We have approximately 150, 180 MSc students starting every year for 18 months program. And we have approximately 120, 130 PhD students at any given time. We are funded partly by Dutch government, 1/3, and 2/3 we earn from projects, from tuition fees and all this. So we are a bit run like a business because we don't have much governmental money, only 1/3. We were established in 1956 by Delft University of Technology, and we have a lot of links with the Delft University of Technology. And by the way, this university was in the Shanghai list of universities, was found to be the #1 in water engineering around the world. So it's an interesting development. So we have 15,000 alumni around the world. Many of them come from Asia and Africa because we're aiming at developing countries. We don't have Dutch students, not too many European students. Most students are coming from developing world. As you see, largest number is from Indonesia. This is how perhaps Dutch are paying debts towards their colonies, and also from many other countries, and even some from Russia, but unfortunately not too many, so we hope to have more students. If you want to study, you're welcome. But it's not cheap, so we have to find a lot of money to come. So we run different master programs and specializations. Our program, Hydroinformatics, you see here, and it's part of so-called water science and engineering master program. Delft is a nice city. If you manage to visit the Netherlands, please come. This is the central marketplace. Opposite there is a church where all the Dutch kings and queens are buried, actually. They're buried in Delft. And only 3 hours and you're in Paris by train. So it's not that far from other interesting places in Europe. A couple of words about the Netherlands. Since we don't meet too often, maybe I would start with this. So this is the Netherlands. You see, this is Rotterdam port. This ship just came from China bringing a lot of stuff. And all this stuff moves with these trucks around Europe. So that's the largest hub in Europe, I think. Rotterdam is the largest port in the world, depending how you count, maybe Singapore as well. So they're competing. And everything is built below sea level. So 1/3 of the country is below sea level. So problem of water management is really acute. So this is an entrance to the Rotterdam harbor. This is storm surge barrier, and it was built 1986. Actually, some parts of it were built in Czech Republic, in Czechoslovakia then, I think still, where they're building nuclear reactors for Russian nuclear plants at the same plant. So, because nowhere in Europe they could have built particular complex engineering devices here. So in case of threat of floods from the sea, so if there is a surge and water is coming into the harbor, these gates would be closed. And they're closed maybe once in 4 or 5 years, only because this threat is not coming too often. But as you can see, the Netherlands is below sea level, so this is the sea or one of the lakes, and this is the dike or levee, Damba. And the roads, many roads are running on the and there is a permanent but very well managed flood risk in the country. So you see this dike is about to break actually over here. So problem is actually dikes, many dikes are not too strong, and especially they become not very strong, strangely, during droughts, when there is a dry weather. Why? They're becoming lighter, and they start to move. So if it's wet, then they're heavy, and they're in place. Interesting development. All right, but let's get to the lecture. So outline would be, I would introduce a notion of hydroinformatics, and then I will speak of optimization, and we'll consider several examples of using optimization concepts in river basin management, groundwater management, and urban systems optimization. And then if we have time, we'll look at advanced topics like using optimization in a multimodal approach and in building machine learning models of uncertainty. As you know, climate is changing, everything is changing, there is urbanization, there are processes that we cannot control even. So this prompts for the developing of water management strategies that take climate and urban development uncertainties into account. So we need more observations, we need more efficient use of data, better predictive modeling tools, and methods to handle uncertainties and communicate it to decision makers, because decision makers don't like uncertainties. So we have to find the ways of doing this. And this is the current focus of something called hydroinformatics. This term was coined by Professor Abbott in the end of the 80s. So he was a co-creator, at least in Europe, of computational hydraulics. So if you want to know more, find his book translated to Russian, which is called «Вычислительная гидравлика». Professor Mas, я думаю, перевел ее. And in the end of the 80s, it became clear that, in fact, many problems of hydraulics, computational hydraulics, have been already solved, and they're encapsulated in software. You can buy software already off the shelf, or you can develop your own software if you want. And he was a visionary, and he thought, okay, what is next for this field of science? And he said, okay, we should look at technological developments in information and communication technology, and he merged these two words into hydroinformatics. Like in bioinformatics, same things are happening in other fields of science, of course. So we define hydroinformatics as modeling, information and communication technology, and computer sciences applied to problems of aquatic environment with the purpose of proper management or better management. So he wrote a book on hydroinformatics in '91, published. So it's a tricky one to read, but if you like to read about philosophers and stuff like this is typical Abbott's style. So we deal with the whole information cycle that integrates data, models, and humans, or decision makers, or stakeholders, or population. So we would like to connect to make this flow of information thing. Okay, let's skip this. So hydroinformatics, in fact, is between instrumentation, modeling, water engineering, environment, but on the other hand, IT, system science, optimization, and management. So it tries to incorporate all these concepts in water management. It would be maybe useful to think about the following, that we are speaking of encapsulation of knowledge related to water. So first type of knowledge, there is tacit or implicit knowledge in, oh, I have a pointer here, embedded within the person, so it's what between your ears, все, что вы знаете. There is also knowledge which is already encapsulated in words, in books, in papers, and everything else. And very often now it's in electronic media. We just discussed that probably nobody reads these books because most of the material nowadays is in electronic form. So the role of libraries even is changing. And then there is something which is encapsulated in mathematical models. And what is encapsulated in models is several hundred years of experience, maybe thousands of years, of practitioners and scientists. And this is all written up as mathematical equations describing water motion or many other processes that we are observing around us in the formulas, algorithms, and computer programs. So all this we would like to integrate and we call this Hydroinformatics system. So all this knowledge integrated under one umbrella. So we move from observations to decisions. We first observe something, then so data and meaning becomes information, and information plus experience, we call it knowledge. And we think that models being run generate new knowledge, not data. Because all this knowledge which is in the models being applied, all the numerical engines, all the mathematical models applied to the data generate new knowledge. So that's what is happening in when we run models. And then we have to generate responses to this. So humans have to make decisions, and we want to make best possible decisions. And this is when we apply optimization. Optimization in itself is not a model. It's a way of choosing the best decision possible. So here it's just an illustration of what I have just said. So we observe Earth using different ways. This guy also observing floods. And then later we could use this data on calibrating our models, by the way. You know that in often restaurant owners, which are typically on ground floor, when there is a flood line, this very important knowledge for people to calibrate the models. Then all this data comes to numerical weather prediction models. This creates hydrological load and hydrological cycle. And then this data is then used to generate the assessments of water levels, of water flows, so states of the system that relate to water, and then decisions are made. What decisions? It could be strategic decisions on where to build houses, not too far, not too close to the rivers if it's a danger of flood, or operational management decisions when to evacuate people during floods, for example. By the way, these people here, who is the decision maker, you think? So questions to the audience now. Let's have a bit of feedback. Who are these people here? Who is the decision maker? Okay, interesting.
Guy in the tie.
Guy in the tie, okay. Well, this guy obviously is not decision maker. He is hydroinformatician that runs the models, okay. Important person, but I'm not sure he can make decisions. But he can prepare decision in such a way that he would push certain decisions which he wants to be chosen somewhere, maybe better colors to use and stuff like this. But perhaps here the woman is the decision maker, the lady. You know that a man is a head, yes, and the woman is the neck, which turns the head whichever direction she likes. You know? Understand the joke? No? Yeah. Yes? Okay, good. So that's okay, good. So that was a joke. Maybe it's not true. Sorry. I should be careful with this type of jokes, yes?
You could be taken to jail in the Netherlands.
Once again, as always, you are right. Yes, I have to stop with these jokes, yes. But here in Russia, we're not that advanced. It's okay? So thank you, yes. So here, it's okay. But I'm positive to both, so head, neck, so it's just... but thank you for the warning. I will not continue in that line. Okay, let's skip this. Storage, let's skip because we don't have much time. So where is data is coming from? So data is coming from, nowadays, from different sources. There are gauges, but a lot is coming from Earth observation, remote sensing. So a lot of data can be downloaded from internet in near real-time fashion. So the satellites give you precipitation forecasts, in fact, not forecasts, but measurements. But some of them, so measurements several hours before it's observed, often of reasonable quality, and radar images give you the images of now, and some of the products make also forecasts of where the weather system would move. It means you get the weather forecasts from radar-based products. So this is changes quite a lot. What do we do with hydraulic and hydrological modeling? Because we're getting better and better data from, it's a large scale. For small scale, still gauging is very important, but for larger scale, remote sensing can serve very well. We also use different types of very important tool, which is called GIS, Geographical Information Systems. It's a tool, but it allows us to georeference a lot what we observe in different layers of GIS, and it helps decision makers to make decisions. Also, computational tools which are based on geostatistics on top of GIS allow you to do quite a lot. So that's very useful tool, very important tool for in water management. Done. Thank you. Now modeling. So modeling is in the heart of hydroinformatics, or the heart of hydroinformatics. So computer-based model is a simplified description of reality and encapsulation of knowledge about a particular physical, social, biological, chemical process that we observe in electronic form. So again, hydroinformatics integrates data, models, and people. So let's talk about modeling for a second. So one of the most important and widely spread tools in modeling is physically based models. So we take the basic principles, which are Newton physics, and we write the differential equations describing the water motion. Can we solve these equations, by the way, analytically? Good, excellent. We cannot. So we use numerical methods to solve these equations approximately, but actually it's enough. Accuracy is enough because data is anyway bad, so it's good. So this process models or physically based models, actually mainstream models which are used everywhere. Another type of models is data-driven or statistical models. So imagine we collect enough data about the surrounding world, and then we can find patterns or trends or relationships between different environmental variables which would then describe the nature. In fact, it's better than to use assumptions, which you use quite a lot in physically based models. Because if we collect enough data about environment, it's a pure picture of environment. It's not subject to assumptions which we always make when we're writing down differential equations. So in fact, in theory, this would be the best way to model. Problem is we don't have enough data, of course. We have only limited points where we measure something, and not always, and accuracy is not terribly high. So that's why these type of models play a complementary role to the physically based models. However, also widely used. Maybe they're not called data-driven. Sometimes they're called empirical, because they're based on experience. Experience is measurement, is observing the nature. And these are also, in a way, data-driven models. But currently, we call them data-driven because modern data-driven models use advances in machine learning and computational intelligence. So you could build complex nonlinear statistical models which could be on par in terms of accuracy with the physically based models. And current trend is combination of both models when we build hybrid models. I hope we'll have time on Wednesday to talk about this. So role of hydroinformatics in addressing water-related issues is in data. We develop technologies to collect data, but also to prepare data for modeling, to store it and analyze. We bring innovation in modeling and forecasting theory. Trying to use actually quite a lot what is done in other areas, like you know, IT, hydroinformatics is technology-driven. We use a lot of developments which have been already applied in other areas of science, in military, in financial services, and elsewhere. So unfortunately, civil engineering on water management is not the first one to use advances in computer science, because other areas have more money, so they develop certain methods geared towards particular areas of science, like finance and military. This is where money is. But not that much money in water management. That's a bit of a problem. So we have to also look at advances made in other areas and borrow their experience and use their experience when we're developing our own models. So I'm talking, for example, time series forecasting. There's a lot has been done, but first it's not for water, it's for other areas. And then optimization of water management. So we want to develop the best possible solutions to implement and not just some approximate. And we have to take into account interests of stakeholders. And this is when we start talking about multi-objective optimization. That's what we'll spend some time in the end. So when do we have a break? 10:30? 10:20. Mm-hmm. So model-based optimization. So that's the main thrust of this lecture. So problems of water-based optimization are many. For example, multi-purpose reservoir operation, groundwater management, resources allocation, models calibration, minimize error, and urban water systems, like drainage system in drainage in the cities. Ливневая канализация, правильно называется? How to optimize its work. Okay, well, we need some mathematics, right? Лев Самуилович, вы почувствуете себя дома.
Много лет занимались на заре гидрологического моделирования калибровкой с помощью методов оптимизации.
Так все уже решено. Что же я тут делаю? Абсолютно правильно. This is a very well known theme. So optimization of function, which is a function of many variables, typically real valued, but not always, by the way. So we want to find the minimum of this function. So this function is two-dimensional space with two inputs, two variables, but typically it's many more variables, so we cannot even depict it. So for example, this x here are reservoir releases. What should be so decision variables are reservoir releases, and we want to maximize hydropower, for example. That's a typical optimization problem. Okay? So in optimization problem, we have to decide about three things. One, what do we want to optimize? So what minimize or maximize? We maximize profit and we minimize costs, for example, okay? Cost-benefit analysis. Second, decision variables. So what are the variables actually that we should include into the optimization problem, which are relevant? And third are constraints. There are always constraining factors that do not allow us to choose variable values as we wish. А у вас была оптимизация вообще в курсах? Да. Как хорошо. А кто читает? А он из какого-то другого факультета, да? А, здорово. Отлично, здорово. Ну, тогда я вообще не знаю, о чем и говорить, потому что вы все знаете. Но давайте, let's look at some details maybe a bit. So the problem is that... Ну да, Розенбрук, да, 60-й год. Yes. So a lot has been done long ago. Да, это точно. Видите, я тут его упомянул. Да. No, but what I want to say, so if f is known analytically and you can find derivatives, you can use derivative-based optimization, which is the best. Okay? So even in complex problems, there is now software that solves problems quite reliably for many hundreds of variables. IBM developed, for example, or HSL, well-known libraries that you can use. However, if f is not analytically expressed, we have a problem because we cannot calculate the derivative. So here, you see, if you know derivative, then you know how to move along this surface down. Surface is not known, you realize. So we can calculate only function here and derivative, and we can move towards the minimum. But if you don't know the derivatives, then where to move? You don't know. You can assess derivatives by using grid search. So you investigate space around you in the space of variables, and then you can find out more or less where to move. So there are some tricks developed around this. And these methods actually listed here. We use Nelder and Mead, which appears to be really good, easy to program, and you can find in numerical recipes the code, which is 20 lines maybe 50, not more than that. And it appears to work very well. So the idea of this method is to indeed evaluate several points around you and then move towards the best point, and then again towards the best point. And then you move in the space of variables towards the point where you have low value of the function. But there is another problem. that this function may have many minima, because functions are very complex. So what to do if the function has many minima? Then we use some randomized search methods, and we'll speak in a second about these methods. Okay, a couple of words about classical optimization. So what do you do here? How to find this minimum? You don't know, you don't have this curve, of course. You have only the formula. You find derivative of this function, because if it's analytically known, in differentiable, you can find the derivatives, and then you solve this equation. In this case, value is 15. This optimizer, this is the value that gives you minimum. Okay, in multidimensional case, you need to find the gradient. So these are partial derivatives of that function, which you have to point to 0. And there are other additional conditions for second derivatives and stuff like this. But it's all solvable. Problems start. So yes, now let's introduce constraints. So if constraints are here, still you have minimum at 15, because the constraints have the point where derivative is 0. But problem starts when situation is this. So if constraints are different, then this is the function that you're investigating, and nowhere in this space between 5 and 10, in this interval, nowhere derivative is 0. This creates big problems in multidimensional spaces. So in fact, you try to hit the boundary and then move along the boundary until you reach a minimum point. So in this case, in one-dimensional case, it's simple. But in multidimensional cases, in the 70s, there were books and books and a lot of research done how to solve nonlinear optimization problem. It's called nonlinear optimization because f is nonlinear, and it's assumed to be differentiable and analytically known and differentiable. But imagine you have a problem where value of the function is not given by a formula like here, but is generated by software. So you have to run a program to calculate f. And you don't know derivatives, because you cannot differentiate software in most cases. And imagine your program runs for 10 minutes to calculate 1 point. What do you do then? So all this is unapplicable. So all the science developed in the 70s for nonlinear optimization is hardly applicable in these cases, because models are complex, functions are not known analytically, there are many if-then-else rules in the software. Even if you can somehow analytically assess what is there, still software is not an easy thing to deal with. Okay, that's about gradient search, what we discussed. So I will not go back to this. I would like to move towards the randomized search methods. So randomized search, in fact, does the following. We simply throw points in the variable space, decision variable space, and we calculate function in each of these points, and then we make a decision where we should throw more points. And we're doing this in a randomized fashion. So let me show me this first, pure random search. So imagine your decision variables x1, x2. So for example, this could be diameters of the pipes you want to choose in a drainage system, or this could be releases of the reservoir, or this could be amount of water that you give to different users in a catchment management, in a water management, some different farmers that demand water. So what do? You generate randomly vectors x1, x2. There are here maybe, I don't know, 50. You calculate function points at u, like this. You calculate function at each of these points. And then you choose the best. That's it. Pure random search. You can do grid search. If you arrange this on a grid, you can also do this. But it has been shown that randomized search is better than grid search. I'm not sure if philosophically it can be explained, but okay, anyway. So that's a pure random search. That's what people do very often. If they don't know anything about the problem, they generate random solutions and choose the best. That's how I think men make decisions, not women. Women are always more strategic thinking, and men make decisions by random choices. And then boom, that's how it is. Okay, but we don't like it. We'll do it a bit more, a bit better. So let me now discuss this randomized search optimization loop. So first we generate the vector of decision variables, these x1, x2 points, or maybe many more than x1, x2. Then we run the model for it. So we calculate f for each of these points, running the model. So it may take minutes, maybe hours. Like in one of the conferences in optimization, a person was listening to all these wonderful talks about how accurate we could be in global optimization when people were using 50,000 runs. And then he stands up and says, I am an engineer from Honda, from Japan. And to run one model, we want to optimize the design of a car. So to run one model, we need 3 days of a supercomputer. 3 days. So what you show is all useless for me, you know. Tell me, how can I optimize the design using limited time when my model runs for 3 days? And then everybody is in silence, and then fortunately it was the last talk, so everybody went to a drink, because you cannot do much more after this statement. So it's a bit, so scientists seems useless for complex problems. Okay, let's forget this. I didn't say this. So then we repeat this loop in a smart fashion. We'll discuss in a second how. And then we stop when optimum is found. Okay, quite simple. So when do we stop now? So if this is x, in this case one-dimensional problem, this is function value. Imagine these are random points we have chosen in some interval. And we advance towards the minimum, and we want to stop at a certain moment. So when do we stop? We stop either if this difference between subsequent consecutive function estimations is small. So we say this, f of xn is vector x at step n minus 1 at previous step. And then we divide by f of xn, and if it's below epsilon, we stop, okay? Relative tolerance. Or we say if these points are too close, we could use this condition as well. Xn minus 1 divided by xn also should be small. Epsilon should be different, epsilon x, okay? So these are tolerances that we have to observe. So we never could reach absolute minimum, but we could find a good assessment of it. So for Honda person, he would need 1, 2, 3, 4, 6 runs, 18 days. But for us, for simple hydraulic modeling or hydrological modeling people, one model run could be maybe minutes or maybe seconds. For simple models, fraction of a second. So it's not that of a problem, actually. So we developed the global optimization tool called Globe. So we generate a vector of decision variables. Then we run the model. In this case, actually, we were optimizing the water distribution system using EPANET. It's a hydraulic modeling system for hydraulic modeling of pressurized pipe networks, very widely used around the world because it's free. So here we could thank American government, at least for something. It's not for the camera, but they give for free quite useful codes. This is one of them. So EPANET. So we generate pipe diameters here. We run EPANET and check heads at different junctions. And if head is okay, we check the constraint. Then it's a good solution, and we save it. And then we generate new solution, and we run this model in a loop using randomized search algorithms, which are implemented here. And then when we're satisfied, we end up with the optimal solution, or several of them, that we could present to the decision makers. So that's what typically is happening now in model-based optimization. This is a standard optimization loop, which is used by many people around the world to optimize systems based on all these components around, purely software, small things that would allow to transform vectors generated by this optimization tool and put it into the internals of the model to run. So so when I first actually heard about randomized search, it was in the beginning of the 90s. I thought, interesting. So, and then everybody was doing genetic algorithms, which was a popular theme and still is. And I thought, interesting idea. So that's we'll not discuss it here. If we have time, we will. But I thought it could be a redundant thing, because it appeared it's not very fast. So it generates quite many solutions which are not needed maybe. So, and then I read enough, and there is a good book of Zhiglavsky on global optimization, 1992, I think, published. And actually, many methods use the same idea. And the idea is this. We first generate a random number of vectors in the space of variables. And then we would leave some of them which are good. It means function value is low. Okay, if function looks at you, so function values here are low, and for these ones are high, we're not interested in them. So that was first idea which I picked up. So we call it reduction. So we reduce number of vectors for the further analysis. And then we could use local search now in the areas which are interesting. If we cluster them, we run cluster analysis here. We cluster them into groups, and we continue search, randomized search for each of them separately. So for example, for this cluster, we generate more dark gray points. It means we generate points in the proximity of this center. You see, for two-dimensional case, we use the box. But for multi-dimensional case, the hypercube is very close in shape to the sphere. Actually, already for five-dimensional spaces, they're very close. In volume, they're very close. So it doesn't matter what to use, boxes or spheres. You can use a sphere here as well. And then we generate more points. And then, actually, we start moving towards the minimum. Because these points are, in fact, a secret estimation of gradients. Because if we know enough points around us, if this is x1, this is x2, no, this is x1, this is x2, yes, and this is the function f. So if I would be generating enough points around me, I would see where function value is low, and I would move there and generate more points around myself, and move that way until I reach the point in vector space which gives me low value of the function. And this is how we continue, and then we stop somewhere. So this algorithm is called adaptive cluster covering, so it's implemented in this globe tool, and we use it quite often for model calibration, for example. Any questions about this? Yes?
What is the ways to generation more points?
Random number generator. Just well, good question actually. For some implementations, I use beta distribution, sort of like this. So you generate maybe more points around the good point and a bit less around, but it appeared it doesn't matter actually. So we use uniform distribution, multiple uniform distribution to generate more points. But we constrained, this cluster is shrinking cluster, you see it's shrinking, shrink the box. So this box is shrinking in size. So every time we're reducing constraint, so we generate more points, and we're getting more and more accurate estimates of the minimum. And then we stop at a certain moment.
Do you use parameter limits also?
So these are parameters. This x1, x2. These are, if we calibrate the hydrological model, these are the parameters. Yes, of course. Exactly. So this is a constraint optimization. We impose, of course, limits, ranges for the parameters to optimize. So we are doing this in a hyperbox, in the box hypercube, which ranges for the parameters are physically based, of course. Yeah. So if we talk about calibration of models, sure. So it's not blind search around that Shizi 10 million. No.
If we use black box model, we can opportunity to pose some limits on parameters.
Yes. So of course.
Model,
yes.
Advantage.
Yeah. When we talk about model calibration, I will speak about this. Yeah. Right. So this is the tool. You can download it somewhere. Forgot now where. Ask me, and I will show you how it runs. Actually, I can show it now. Sorry. Okay. Yes. So 5 minutes. I will start this. So we have a hydrological system to model. Okay. Hydrological modeling. You know all this. So I will just briefly repeat. So this is the natural system which we want to model. So we write mathematical equations and use all our knowledge. And there are different modeling systems which are in use right now. So for one of them is started in UK actually, and then DHI took the code and developed Mike Shi. So that's an integrated system with many components implemented. It's not only hydrological, but also hydraulic. There are lakes. There is Mike 11 here in the middle running for rivers if you need. So it's an integrated system that groundwater and surface water and everything else. So it's integrated system where a lot is done. It's expensive, but some people do use it. Now you can see it's distributed model. So it tries to mimic the natural system as close as possible. So it means these cells typically should be small if you want to model the natural system well. This is a famous EcoMag system. Юрий Георгиевич, вы можете вот изучить вашу систему, если вы хотите. So there is a reference I found. Yesterday I tried to find on internet a bit more details. I found only one paper in 1999 with Gottschalk and others where some of the details are given. So this is also a distributed system. It's only hydrology. There are no rivers, right? Yeah, no rivers. Also rivers. Okay, so it's also integrated system. So one of the system which will be used in this project, which funds for this school. So we should give reference to this system, isn't it? So and this I picked up from that publication which I have shown. This shows that precipitation you see is given per cell or per region. So it's not one gauge, but you need input to the model coming from many points. Where do you get it, I wonder? So it means you need interpolation between gauging. So because you have only 3 gauges here, 1, 2, 3 here, but you have to interpolate. And interpolation could be very tricky because in the kriging, if you change one parameter a bit, you can get completely different fields. Or you get data from remote sensing, but then it's not immediate. It's near real time, but it's not real time. Okay, it's one thing. And the evaporation or evapotranspiration also, you have to know it per cell. That's a problem of distributed models. They're very nice, but they need a lot of data. Question is, where do you get the data? So in a very well-studied catchments, you have this data. In poorly gauged catchments, you don't have this data. But then you have runoff. These are runoff outputs. Yes, Yuri Georgich? You see how many runoffs you have? So these cells are connected. So you don't have runoff only at the outlet, как-то створ, but also at many places. And this is the model states. It's internal state, soil moisture. It's a state of the model. You can say also it's an output, but in fact it's a model state. So you have input, you have internal states, and you have the output. So input is precipitation, evapotranspiration. States are the soil moisture. And output is runoff. The Как это будет по-русски? Stock. Большое спасибо. However, for many cases, we don't have that much data. That's a bit of a problem. So we build simplified models, tank models. Lumped, conceptual rainfall runoff models. Okay? So we assume the whole catchment in its complexity is represented by only one column, which averages everything across everything. And we have a sequence of tanks, and in different countries at different times, so these reservoirs are connected in different forms. And we have many different models. Sorry, I should have used, of course, mentioned the French model. Sorry, it's very nice, only 4-parameter model, jour for the daily and the hourly. So, yes, H, and the first 2 letters. GR4 model. That's also a reference. Professor Andreasyan could give you more details because it's developed in your department. Right, okay, so it's one of them. But also tank model of Sugawara, which was developed in 1961, one of the first models. I'm sure in Russia there were also similar models developed, just don't know of them. NAM of DHI is also a simple model, and HBV developed in Sweden, widely used in Europe. Snow melt is not very well represented, but okay. Other scientists write up components. And so this is a tank model of Sugawara, which we used as an exercise. Very simple model, deliberately simple, to have not too many parameters. So look, this model is really simple. So this is the input rainfall evapotranspiration. So it's a top tank, which represents surface flow. And you see these equations for runoff here are linear. Okay, it's all linear equations. You can say linear reservoir, but there are two outlets, so it becomes piecewise linear as water level goes up. So this initial water level. And then it percolates somewhere to sort of base flow or groundwater flow, whatever you call it, intermediate tank, which also is linear reservoir with the linear dependency of flow on level. So H is water level in this tank, or soil moisture, you can say. So it's a linear model. So it's a very simple model of Sugawara. And Sugawara himself was, Andras Solomatine was telling me when he was working at YASA how Sugawara was calibrating it. So he knew, here he had a procedure to calibrate. And every 5 minutes he would get the result. He would say, oh, and then oh, and in this, whoa. So he would do 100 runs. And then in the end, he would arrive to some useful coefficients. And these coefficients to calibrate. So first conveyance coefficients, which are here, coefficients of proportionality, K1, K2, K3, K4. See these coefficients? They indicate property of soil. In fact, initial levels, these are initial conditions, also unknown. We don't know them. And again, this simple reservoir represents the whole catchment. It could be several kilometers, square kilometers, could be several thousand square kilometers. Whole catchment. Why we can do it? Because we're interested only in the total runoff. So we're interested only in one variable which is aggregating the whole complexity of this natural system. We're not interested in runoffs in these cells, as I have shown before. We're interested only in one runoff. Because very often it's enough. If you want to know what would be the flood downstream, you could maybe live quite well with the very simple model. And question is to you, can you measure these coefficients? Measure. Lump conceptual. Lump, like lump of sugar, кусок сахара. Это один кусок. Кусковая модель. Как она по-русски называется, я даже не знаю. Вот. Я много чего изучу сегодня. Можно ли измерить эти параметры? Ну, конечно, нет. Как мы их измерим, если это один параметр на водосбор, который... Ну, вот. Сейчас мы... Да, можно. Ну, короче, измерить их нельзя, потому что у них нет физического смысла. This is an aggregated parameter that takes up everything in, and it's just used as a coefficient of proportionality calculating this internal flow. Also, this flow doesn't exist because it's aggregated, some sort of average flow. Okay? What we can measure only this. We can measure only input evapotranspiration to some extent and total runoff. That's it. So how to find these parameters? By trial and error. We call it calibration, или мы называем это уточнением параметров. Как вот нам вчера представили, позавчера, в одном из диссертаций. Ну, я исчерпал свое время. Перерыв? Yes? The break. The most interesting part of any conference is the break. 5-minute break. So what is calibration? First, what is a good model? No, you maybe know all this. So good model is the model that represents reality well, right? So just a natural thing to think of. So how do we calibrate? Of course, we use hydrological judgment. We think of the system. We go to the field and all this stuff. So calibration is not a blind process. It's only complementary towards the judgment of a hydrologist. Okay? То есть вот гидролог, он должен сначала подумать, а потом уже вот эти все странные вещи использовать. But in the end, what we want that on the past data, so we need past data for calibration, that model output is close to the model, to the natural output, what we measure. In this case, flow should be similar to what was measured. Okay, so we compare two time series. So if we want to use automatic tools or semi-automatic tools that I've shown, Then we have to measure the quality of the model using different ways: root mean squared error, mean error, Nash-Sutcliffe coefficient, efficiency. So here we actually take the mean squared error, as you see, just not dividing it by t. So it's not mean but total. Okay, anyway, but we divide it by the variance. Okay, and then we also could use a bit more sophisticated things. For example, for root mean squared error, we could use here a weight that, for example, would punish even more errors on peaks. So if you want to work for the floods, of course, peaks are important for flood modeling, so we want to give high value, high weight for the peaks. Of course, the peaks are squared here, so in fact, if it's above 1, then the square already gives you high value for large differences. But if you want to stress particular moments in time, you can do this. You also should look at water balance, for example, so it could be accurate, but if you lose water in the catchment in the model, it's not good, or you get water from somewhere, also not good, so you have to do this. Or you could look at time to peak, so maybe you're not terribly interested in reproducing flows every moment, but you are interested in forecasting problems to estimate when this peak will happen, and then your model should be differently calibrated, perhaps. So different ways to do it. In two-dimensional model, of course, you have to look, so if this is hydraulic inundation model, two-dimensional model, then you want that depth at every pixel is what is observed. Often you don't have full data, so you should look at depth, velocity, and residence time. So that's important. Residence time and flood is important because it creates health problems. If water stays for 3 days, then you may have big health problems. So that's also important to reproduce well. So you see, you can use different objective functions to estimate quality of the model. Now, if we use automatic tools here, again, this optimization loop is here. So this is physical system. Y here is the flow, discharge, and model gives you estimate of the discharge. Caret means estimate. So we calculate error some way or the other, as I shown. If error is small, we stop. If not, we continue optimization loop to run the model along this loop over here. Okay, so this optimization loop if we solve a calibration problem. Again, so the calibration is optimization problem. So where are the parameters? Parameters, so this is observed flow. O here stands for observed. M stands for modeled. So parameters are inside this model because QM is generated by the model, and the model needs these parameters to be known, and we don't know them, so we have to find them. So that's optimization problem. These are decision variables that you have to find, and optimization is to minimize root mean squared error in this case. So I promised you to show this thing. Now I found it where it is. So let me show you. So we are, in this case, I'm running globe to calibrate it was too quick, right? Have you noticed anything? Can you explain what's happening? Okay, let me do it again. Let me close this and start again. Here. So what this tool is doing is this, that I have implementation of this tank model, and this tool generates, there are 8 parameters to calibrate, 8 which we don't know, and we run this model hundreds of times in a loop, every time generating new vector of parameters, 8 numbers, running the model and calculating the error. And we use adaptive cluster covering algorithm that I explained, or we can use genetic algorithm or anything else. Okay, so now I will start optimization, and here you have buttons which we could run in a step. So first we evaluate initial population of 104 models. Now what you see on the screen here are, it's an 8-dimensional space, don't forget, so we cannot display it. So we're displaying the projections of 8-dimensional space on planes. This is plane x1, x2. It's 2 parameters of the model, x2, x3, x3, x4, and so on. And I don't have 7 and 8 because I ran out of space. So you can see only 6 parameters, but you can choose what you want to see. So first we evaluate 104 parameters, and this is the best model we found. So initial population 104. So we run the model 104 times. The white points, you can hardly see them, but they're there on the black. On my screen you can see them well, but here, well, maybe you see some sort of small stars here. So these points represent, each point represent 1 point in 8-dimensional space for which we calculated model error value. And yellow point, it's a 1 point in 8-dimensional space, which represents the best model so far. I would say the best vector of parameters found so far. Best means with the lowest error. Okay. Now, if you remember the algorithm, we cluster we find several clusters in this space. In this case, we find 4 clusters. Yeah, you cannot see it, but in fact, they are found here, shown by color, but it's too much light in this room. And you see here, do you see the blue box here? Vaguely. So this is first cluster in which you would zoom in to find the best possible value for that particular cluster, again in 8-dimensional space. So we move more and more. Maybe I show you on this screen if I could. Can you see it here? Maybe better? No? Okay. Oh, there is a camera, so I have to. Okay, and then we move further away. More. You see where every time the cluster becomes smaller and smaller. So in fact, you can see on big screen as well. So in this way, we would move in the space towards the point with the small error. So you see the small square here. That's where we are right now, in this 8-dimensional space. Okay, we could continue this with another cluster, green one. Move. We'll continue. Okay, say don't pause. And in the end, we find the best possible point. So it's this vector of parameters which is listed here. It's also saved in the file. 8 numbers which represent these 8 parameters that we were talking about in this Sugawara model. So as you see, we can use now randomized search optimization here to find the best possible parameters for the model. And you can plug in any model here. Just in the specification file, you specify the model that you want to run. You need to write software that calculates error, of course, and then you have it. Any questions? No questions. So either everything is clear or nothing is clear. So shift F5. Right. Yes, and this figure actually shows this is a model run before calibration. You see the hydrographs are quite far from each other. And after calibration, you see you have much better match between 2 hydrographs, observed and modeled. Okay, so it's a result of calibration. Now, where the hydrological knowledge comes in, it comes in the experience, because these are lumped parameters. You understand, they cannot be measured. So you have to have some experience with these models. Otherwise, you would be doing strange things. You may find completely physically unrealistic parameters, which would still strangely give you a small error, but it's wrong. Even if error is small and parameter values are physical, you should not use them if they not have physical interpretation. So again, first is hydrological knowledge, or simply knowledge, and second is tools that help you, in fact, to run models in a structured way many hundreds of times. Now, let's move to something else. And something else is optimization of water systems. So first example was simple. It's an optimization of a model. So we're optimizing the model. Optimal model means it's a best model. By the way, it's good Professor Bavin is not present, because otherwise he would throw at me something, because there are hydrologists that think that it's a bad thing to find the best model. Why? Because data is not very good. So look, we're trying to fit the model observed data, right? So this observed data, how good is it actually, this observed data? Maybe in a experimental catchment, how your catchment is called in Yakutsk. Maybe there you measure the station, Shipitovka, how is it called? Shostakovka. So maybe at that station, at experimental catchment, you have very accurate measurements of flow. But in many other cases, you don't have good data. So perhaps you are trying to match the model data which is wrong. Then the whole exercise is wrong, isn't it? You shouldn't be doing this. Also, you, of course, are aware, you are all hydrologists, that often you don't measure the flow. You measure the level in a river. You measure the water level. And then you use rating curve. Как это будет по-русски? Какая кривая? Кривая расхода. Вот то мне больше нравится. Как это называется? Эпатаж. Да, это была шутка. Да, значит, кривая расхода, да. Да, это был просто эпатаж, виноват, да. Значит, кривая расхода. А кривая расхода на чем базируется? На нескольких измерениях. Так, сколько у вас измерений для высокого значения потока?
Несколько это мало, конечно.
Вот, очень мало.
Но немного.
Немного. Да, то есть кривая нарисована так, чтобы она красивой была, а там точки вокруг нее, вообще говоря. То есть мы рассчитываем поток вообще неправильный. И бывают ошибки, которые в несколько раз на самом деле отличаются от реального потока. Поэтому, sorry, I switched to Russian, sorry. So be careful when you're doing calibration. Experienced hydrologists would tell you more. I'm not an experienced hydrologist, so you please be aware that model calibration, some people say, is not should not be done at all, because data is not good. So there is a paper of Jean Kunsch on data and models in Journal of Hydroinformatics 15 years ago, where he says it's not about hydrological models, it's about hydraulic models. He says, please don't calibrate river models, because actually all data is wrong, so you better measure well the cross sections and roughnesses and use your judgment.
It's necessary
into account. So it's a...
is the main thing.
Yes. So there are hydrologists that think measurement the main thing, others may think a bit different, but main statement is that use combination of things. Never use one like this. Yes?
But this argument against calibration, it reminds me in some way my own children who did not want to learn their math class because the teacher was so poor and boring, etc., etc., etc. The fact that the teacher or the measurement is not good does not necessarily mean that they should not learn their lessons. And in my opinion, when you build a model, if you start criticizing the data, then you are, as a scientist, you are dead, because you become the only reference. You become God, or you become somebody in love with your model. And even if the data is very bad, I mean, don't laugh at me. There are so many scientists which are in love with their model. Of course, they are human. It's not the case of the weakness. That's why it's also very dangerous to criticize what you're supposed to compare yourself to. In the case of German, it was dangerous.
Yes, even in France. So you have bad mathematics teachers. That's interesting. Yes, very right. Thank you. So, but when you change the teacher, it means you get better observations, right? So the lesson is to, of course, to get more observations and better quality. That's for sure, without any doubt. Could I add to when you tell people who measured data that they're bad, you are dead also for that reason, right? So it's not good to go to the water management people and say your data is bad, so you're all useless. Dangerous, yes. A very good point. Yes.
Whatever is your model, whatever is your uncertainty, whatever is your data, you have to make one decision. Remember this. You have to take a decision. You have to provide one design only. So the work has to be done.
Yes, one decision means you have to fix parameters at one value. Yeah. But when I started to talk about Bayesian, idea is that since data is not very accurate, there are many uncertainties. Why don't we stay with 10 models or 100 models? It means 10 vectors of parameters. Okay, but practice is different. In practice, people like to use one model. You are very right. With one set of parameters, they fix it and use it for several years without recalibration, right? That's the practice. Scientists invent interesting ideas of using ensembles of models. We could do this as well. We'll talk about this. Also possible. But practice currently is one model. Very right. So, and if you cannot show that your model is close to observations, it's also not good. So calibration is important part of any modeling exercise.
Does this lead us to the question to validate the model? You calibrate the model and then you take...
Excellent point. And on Wednesday, we'll talk about this. Very good. Yes, indeed. You are very right. So it's purely optimization. Good point. Okay, let's discuss it for 1 second now. So this model is good for this set of data. But will it be good for another set of data? That's a question. It's called verification or validation or testing. All the same. Okay? So we need secret data set, which the modeler wouldn't see, to test. Why the modeler shouldn't see the secret data set? Tell me. To test the model.
We'll try to take the parameters from
Of course. Then we will calibrate model on the test set, and we're good. So it's unfair. So that's why this test is secret. Test set is secret. It should not be given to a modeler. Modeler should get one test set, one set, which is called calibration set or training set, which would the person, he or she, could use for the model calibration, and then decision maker would produce a secret test and say, okay, this is the new data set, show me that your model is good. But it would be unfair not to put floods here and to put very high flows in the test set. It's unfair because, of course, your model may not perform well on very extreme data. So fair is to split your data into blocks which would have enough low flows and high flows in each block, okay, and then to train it on one block and to test it on another block. That's theory of modeling. But we'll talk about this on Wednesday. Good, let's move on because I have limited time, right? Optimization of water systems. So one of the interesting problems is optimization of reservoir releases. So releases are how much water you release through the turbines or simply release into the river. So on the left-hand side, you have a reservoir, and it has certain volume, and volume changes in time. And you have inflow, by the way. So forecasting inflow is an interesting problem. How much water comes into the reservoir from different sources, you have to know. Also when building it, but also when operating it. So optimization here is to find releases such that your reservoir would work well. What does it mean? Well, for example, producing hydropower generation, a lot of hydropower, but not only. So something which you perhaps know is dynamic programming. We have no time to cover it. It's a traditional way to solve sequential problems. Sequential means that these releases are connected because it's a sequence of decisions made every time step, for example, for 52 weeks. We have to tell the operators what should be the releases for 52 weeks. Last 10, 20 years, this problem changed. Why? Because in many countries, price for energy is determined every second. In France, it's a market of, for example, so market of energy. So you don't know the price for energy in advance. So you cannot optimize really. You can optimize in general, but you cannot optimize for midterm decisions or for a year. In countries where price of energy is fixed, you can do much more. But currently, you switch to other ways of optimization, model predictive control, and all this, which would only optimize short term. But you need to know also long term, approximately forecast for the energy price. So still, okay, we unfortunately don't have time. So in fact, what you want to develop here in dynamic programming, a trajectory. So this is the reservoir volume over here, and you release every time certain amount of water until you reach some final state of the reservoir. Question is, what are these releases at each time step, so that overall your function is maximized or minimized. That's a dynamic programming. Okay? Bellman in 1952 formulated principle of optimality. Pantragin also formulated principle of optimality, who is academician working in Вычислительный центр Академии наук. Okay, anyway, we have to move on, unfortunately. А?
Там была специальная лаборатория, которая...
Да, да. В оптимизации советская наука достигла огромных успехов. В гидропроекте там вообще в 70-е годы много задач решалось на самом деле, потому что гидротехническое строительство было очень развито и нужно было решать задачи оптимизации. Очень много было сделано. Sorry, that was Russian. So it's just I'm opening a window, and if you want to know more, there's a library nearby. Take a book, read about it, right? Now let's talk about for the multi-objective optimization, многокритериальная оптимизация. We have talked about single objective optimization, means we have only one function, but life is more difficult. So in life, we have many functions to optimize, okay, list of functions. So for example, in reservoir optimization, we could optimize power generated, irrigation, water coming for irrigation, and navigability, you need ecological flow, or navigability, you need certain depth in the river downstream, so that ships would move, and also not too low flow and not too low level of reservoir. So that's these objective functions are conflicting. Optimal solution for energy could mean bad solution for irrigation and farmers. Water allocation, irrigation against water supply to cities. What is first? Perhaps water supply is first, but then farmers rebel, and so we have again conflicting objectives. Pipe network optimization. So want to change drainage pipes or sewer pipes in a city. How? It's expensive, very expensive undertaking, but want to reduce flood damage. Flood damage is also high. So which pipes to dig and change and which not? Optimization problem. Model calibration. Again, also multi-objective optimization. Models good on average or good for forecasting floods. So they're not really conflicting objectives, but not exactly the same. So as you see in life, you have multiple objectives at the same time to have in your mind. So what we have graphically, this is decision variable space. So here you have n variables. For example, for a reservoir, this could be 52 releases for the coming 52 weeks in a year. So you have to know value for each week. It's approximate schedule, of course. It will not be exactly followed, but it's what you want to develop, at least as a plan. Okay? So each point is a possible release schedule, because each point means 52 numbers, or n numbers in general. Okay? Now, each schedule is evaluated. My animation works. There must be a big arrow coming out. Yes, that's it. So for each schedule, or for each decision variables vector, we run a model to evaluate quality of this particular schedule. Model calculates this f, function f, but there are several. In this case, two, objective function 1, objective function 2. So if we calculate two function values for each of these schedules, you would have the same number of points over here, and each of them would have two values here, OF1, OF2, which would mean, for example, in reservoir release, this could be quality in terms of navigability, and this is quality in terms of power generation. In case of urban pipe networks, this could mean costs, which we want to minimize, and this could mean flood damage, which we also could want to minimize. So this ideal point doesn't exist. We cannot spend 0 rubles and to have 0 floods. You have to spend some money, then you have less floods, right? So this ideal point we're aiming at, but it doesn't exist. So overall, this assessment is here, but you can see that if you take these two solutions are actually here. These are evaluations of solutions. You would see that this solution dominates this one. Why? Because gray solution is better with respect to both objectives. So this is no sense to look at it because it's dominated by this one. If we do simple exercise of finding the solutions which are dominating all other solutions, we'd end up with something called Pareto set. So this set gives you solutions, and this you can remove, and these solutions to present to decision maker. And then we have to make choices. So how to make the choice of best solution? So this solution is expensive, but leads to less floods, less flood damage. This solution is not very expensive, but it's a lot of flooding. So how to choose the solution? This could be a compromise. Not too expensive and not too much flood. That's a compromise. If you say compromise is closest to ideal, you can formulate the problem as a single objective optimization problem, simply finding one solution which is closest to ideal point. Okay, simply. And then you solve single objective optimization problem, which is often done. Not a good way, but it could be faster. Right. So let's consider an example from this theme. A student from Venezuela brought a problem of Apure. So they have a hydropower construction in Apure River, which is a tributary to Orinoco. Okay, this is schematization, this is Apure River, and they're building hydropower dams here. And it was published some time ago. Actually, I think it was maybe for the first paper where we used neural network to represent hydraulic model. It was a meta-modeling approach, but let's talk about this for a second. So this is a large basin. Okay, this schematization. So we want to find optimal release schedules for these 3 hydropower dams in such a way that, first, we minimize time on non-navigable situation downstream. It's 200 kilometers here. And we measure water level in a river at 3 points here. And water level should be for 7 months above 2 meters. Then they say, okay, it's fine. Okay? And at the same time, we want to either maximize power generation or to minimize the difference between target and achieved production lines. Because we cannot generate too much power because the grids would not be able to accommodate it. So we want to follow certain target line in power generation. So in fact, it's again minimization problem. We want to follow the target line. So it's two objective optimization problem. Okay, 2 objectives. We want to maximize time of navigability or minimize time of non-navigability just to make it both minimizable and minimize difference from the target. So 2 objectives. So one objective is energy, second objective is navigation, and the decision variables are the 52 releases from reservoirs. Okay. So what we did, again, so we showed this already, so it's the same picture. And what we did, we simplified the problem. We switched to single objective optimization problem and used dynamic programming. And what we did, we said, okay, if navigability for 7 months is above 2 months, we don't care. Sorry, above 2 meters, water level in the river, we don't care then. Then any solution would do. So we moved one objective function into a constraint. So we said all solutions here with the objective function value below this threshold are all good, and these are all bad. In this way, if we solve problem only for Z1, for this objective function, we choose this solution and not this one. This is better for Z1, but we exceed the threshold, so it's not good. So then we're solving single objective optimization problem. So that was a conversion of 2 objective optimization problem into single objective, 1 objective only. And we used dynamic programming. The problem was that to evaluate the water level in the river, we need to run Mike 11 model. So NUM model was set up. NUM is also tank model, in fact, the lumped conceptual model. There were 25 subcatchments in this river basins, small subcatchments, modeled by this NUM model, and they were supplying river they were supplying water into the river as tributaries, sort of. And Mike 11 was running the river downstream, full-fledged Mike 11 model run. So it took time. So problem was, it was done in '95 actually, long ago. The problem was Mike 11 at that moment, it's a hydraulic model, one-dimensional hydraulic modeling. We couldn't run it in a loop, in an optimization loop. Because DHI software needed to click you with the buttons and all this, so we wrote to DHI, they sent a diskette. Huh? It was 20 years ago, so you were not born then. So that there was a Stone Age, you know, Stone Age. Yes. So software was not as developed as now. So you had to click things. But DHI does it deliberately not to allow you to develop tools around their tools, because they want to develop tools around their tools, optimization tools, for example. So they're doing it well. But it's not easy to find out how to run the computational engine in DHI tools. In other tools, yes, but in DHI, it's not easy. So there is a non-published secret command line, which we know now, because they're friends of us for research. They gave us this line. We know how to do it. At that time, we didn't know. So then I had strange idea, why don't we emulate Mike 11 by neural network? So we'd run Mike 11 offline and develop statistical model that would link inputs to the water levels at 3 points. Anyway, but before neural network, we had to run Mike 11 in an optimization loop using dynamic programming. Why we need Mike 11? Again, to calculate water levels. Of course, we could have used routing or something else in a simpler way, but anyway, we wanted to do it like this with Mike 11. So problem was Mike 11 was too slow, hydraulic model, and cannot be put in optimization loop because of software constraints simply. So that was our problem. In the end, what we did, we ran Mike 11 offline, so not in optimization, but for different, many different inputs. So the student, Avila Torres, spent days and weeks on running offline manually, generating enough data, and then we trained neural network over here and put it instead of Mike 11. Oops. So instead of Mike 11, we use neural network here, emulating behavior of a hydraulic model. Neural network runs for a fraction of a second because it's very simple algebraic equation. And then you can run this thing for thousands of times without any problem. Over here. On Wednesday, I'll show you this neural network, in fact, which emulates Mike 11. And that was a use of so-called meta-modeling. Meta means model of a model. Модель модели. О surrogate model. Суррогатная модель. Модель, которая заменяет сложную гидравлическую модель простым уравнением из нейронной сети или из статистической модели. Могла быть здесь и линейная модель. Ну, линейная на самом деле была плохая, поэтому мы стали использовать нейронную сеть. So neural network was put in. So neural network is also optimization, by the way. Anyway, so optimization happened here, and in the end we found the solution that was optimal with respect to hydropower generation and was giving us navigability more than 7 months downstream. So that was problem solved using optimization algorithms. So here we combine dynamic programming, multi-objective optimization, and surrogate model emulating hydraulic model. Второй пример, second example of using optimization algorithms is for groundwater pumping strategy for plume removal. So we used ACO algorithm that I have shown you. We call it global optimization algorithm. Why global? Because it tries to avoid local minima. So local means if you have function like this is local minimum, but it may be that you have global minimum, which has much better function value. So remediation strategy was, so it was actually done for 2 catchments, one in California where they're producing electronic equipment and dumping a lot of bad stuff into groundwater. For ages they were doing this, and then in the end of the 80s, they realized, ooh, we pollute the environment, so the legislation in California changed, so they had to start cleaning up the mess. So how to do it? So you could pump the clean water into this, groundwater moves, and you would gradually pump out the polluted waters. And another catchment was in the Czech Republic, Czechoslovakia. Then? No, already not, Czech Republic. So 2 publications if you want to know details. And we also used approximation of groundwater. That was ModFlow. Do you know ModFlow model? No? It's a complex groundwater modeling system, free for download. You can use it for free. Not very good interface. If you want to buy interface, you buy it. But of course, we have EcoMag and other models to use. Yes or not? Groundwater. Anyway, so there are different models to use. So, but it's very slow. So what we did in this paper, we replicated it again by neural network. So we put very fast neural network into optimization loop, and we were able to find the best solutions. So I have to move quick here. So that was a plume which we had to remove. We used ModFlow, and ModFlow allows, so there are methods implemented, particle tracking. We throw virtual particle into the water, it moves, and then when 95% of particles are moved out, then we're happy, it means all clean, okay? So that's by injection and extraction of water. This is how you move. Okay, let's skip this. So we had 2 objective functions. First, minimize cleanup time. Second, minimize cleanup cost. If we want to do it quickly, it costs a lot. So if budgets are limited, we have to find a compromise solution for this. So this is, by the way, cleanup rate, objective function. So cleanup rate. And these are different parameters in positioning of the wells and pumping rates. So we have to decide how much to pump, it costs money, and where. You see how complex the surface is. So minimum is somewhere here, but if you choose this one, it's also a minimum, but it's a local one. It's a very complex optimization problem, actually. And it's not analytically known, because to calculate each point on this grid, we had to run ModFlow. So each point is one ModFlow run, which takes minutes. So this took several days to calculate this plot. Again, we use adaptive cluster covering, as I showed. And this is our optimization loop. So this is ModFlow model over here. This is globe algorithm. So we're running it in a loop until the minimum value of the objective function found. And in another paper, again, as I said, we run ModFlow offline, generate statistical model or nonlinear statistical model, which is neural network, and then put it in optimization loop instead of ModFlow, and we can run it much faster, many times. So that's use of meta modeling in model-based optimization when model is really complex and needs a lot of time to run. Okay, let me skip this. So that's in the end what happened. When do we have a break? In 5 minutes? 2 minutes? 5. Okay, urban drainage network optimization. So a problem is floods, urban floods. A lot of damage, as you know. Why it's happening? Because the drainage systems are not adequate. They cannot handle enough water. Also hydrology, urban hydrology changes. Everything is paved, no parks anymore, no soil that would accommodate a lot of water. All bad. Also, of course, people build houses where they shouldn't be built. In Athens, we were in a project, by the way, maybe you know, with Kusis 15 years ago now, when we looked at the map, and there are drainage canals, and then there are small dashed lines on the map across the drainage canal. And we ask, what is this? You know, drainage canals, because it's a flash flood system, comes from Mediterranean, hits the mountains, and the Kufusis, the catchment is flooded, and Athens is flooded because it's downstream. It happens in 3 hours, you have a flood after the rainfall. So 20 fatalities, you see, so it's a big problem. But then there are some drainage canals, okay, nice, urban planning was good, but there are small dashed lines on the map. What is this dashed line, we ask municipality. And they, sorry, people built houses in the middle of the drainage canal. Sorry, that happens everywhere. In Taiwan, we know houses are built in the 70s in the floodplains and a lot of floods, right? So that's happening everywhere. By the way, do you know where the flood management authorities locate their offices? In good houses, because they're important people. The very nice houses in the European cities. And where the very nice houses in European cities are built? Close to the river, isn't it? And where do they put their computers? In the basement, because this is where computers should be. So what is flooded first? Of course, the computers that run flood models. So that's a common place in England, for example. That's quite well known. So first thing which is flooded is Water Management Authority with their computers. In Athens, observatory is on the mountain, so that's where it should be on the mountain, so it's something else. Okay, anyway, what do we optimize in here? So we want to optimize the pipes which we want to change. A rehabilitation problem, either design problem, which pipes to put, or rehabilitation problems, which pipes to change. Because pipes are old in most cities. In new cities, they're new, so we can design well. So we use mouse system, which is from DHI, or we could use SWIM system, again from the Environmental Protection Agency, SWIM, SWMM, freely for download, very good system. So if you want to use it, you can do it. So flood damage functions, as you know, we can calculate floods based on inundation areas. We can calculate flood damages, and this would be our objective function, which we want to minimize, right? So what is then the variables, decision variables in this problem? Decision variables are the pipes to change and diameters of the pipes. Which diameters to put? Big pipes are expensive. Why don't we put small pipes? It's cheaper, but not much conveyance, so maybe we still have floods. So this objective function we could choose. Again, model-based. So these are objective functions. So rehabilitation costs, pipe renewal, and flooding damages, which can be calculated if you know how to do it. Often it's not easy. Same thing we do. Same optimization loop. We run optimization procedure, and we run the wastewater system pipe or drainage pipes, mouse or SWIM or any other model. Again, the model-based. Again, in our research, we also use meta models, because to run SWIM for large network takes a lot of time. So we could run it offline, and then gradually we retrain neural network as we get more data. So we develop this more Prism algorithm that does it. Okay, let me show you. Let me now move to presentations. Oh, how to run this? What is it? Sorry, it's first run. So this is real stuff. You see by color, the pipes which are being changed by different diameters are shown. It's just animation of the optimization process, simple case of 12 pipes. So randomized search in the space of all possible diameters for 12 pipes, 12-dimensional space. For every decision for pipes, we evaluate quality of this solution, and then we continue. And in the end, we arrive to the set of pipes, which would be not too expensive, and which would lead to small flood damage. Okay, so we have to get to the end, isn't it? So this is Pareto set, which we generated. And one more, say we had a project with Italian partners. This is City of Milan with 118,000 pipes. And we developed an optimization algorithm which had to first split it into blocks and then do optimization. So our optimization was running full network. Our optimization was running for 30 days. 30 days of run on a not supercomputer, but on a cloud. So we were running around 50 computers generated on the cloud, but actually it was Surfstar supercomputing center where you generate Windows virtual machines and then you distribute the optimization. And this in 5-dimensional space, 5 objective functions were considered. These are different solutions. So it's yet another example where optimization algorithms, in fact, randomized search algorithms for multi-objective optimization can be used for water-related problems. Yes?
What is better? In this case, use simulation approach
Yes.
or optimization?
But it's combination. So simulation simulates the system, like river or water distribution system. If we put parameters, we run one simulation, fine. But then we want to choose the best parameters, and this is then optimization. So it's optimization simulation.
It's impossible to optimize such complicated things.
118,000 pipes. In 30 days, we get optimal solution. So it's Water of Milan, Water Authority of Milan. They're so happy about this. Never did this before. So our PhD student did this for them.
And you can trust the result?
Yes. You can see that the results are better. Water heads are above. Reservoir management is better because they're getting water from reservoirs, 5 reservoirs in Milan. So it's a very complex system, so optimized by computer-based optimization. Colleagues, I have to I have many more examples to show. Okay, water management in the Netherlands. Okay, the rest is maybe more advanced stuff, and we have time. We could talk about this. Okay, let me conclude. Conclusion. So why do we need optimization? Well, water systems are expensive, so it's better to optimize, because if it costs 1 billion of euros, 1% of 1 billion is enough money to think about, okay? And the researcher's time doesn't cost so much as infrastructural work. So invitation to all infrastructural management to allocate some time for research, for optimization. So again, for water systems, most things are done with models, so we have to use model-based optimization and not traditional ways of optimizing things when functions are known analytically. In rare cases it's possible, but in most cases not. So we have to use global direct optimization or randomized search methods because we're driven by the necessity to run models, model-based optimization. Now, yet another thing. We have to change our way of thinking and move towards multi-objective optimization. So, because very often we pose one objective which we know quite well, but there are many other objectives. Often they're put in constraints, yes, but better is to generate Pareto set of solutions and only then to move to constraints. So Pareto set gives the decision maker, say, 10 possible solutions to discuss, or maybe 3, and then it creates discussion around these solutions. It's a very important component of any water management decision when there is discussion, because then different alternative ways of view come in, and you can discuss differences between these solutions, because it's difficult to choose one out of several which are uncomparable, because they're all good from the Pareto set. And we say that optimization constitutes an important part of hydroinformatics technology, and I invite hydrologists to have this in mind, because if you're doing your hydrology, in the end, your hydrological models or understanding of hydrology of different natural systems, in the end will be used by decision makers that will have to make some decisions, and decisions are made based on optimization. So maybe it's for you interesting area to move into when you would know natural systems so well you can bring in knowledge of a natural system into optimization. That's important because it's not automatic. Humans are always present in these optimization loops. With this, thank you, exhausted my time. Thank you very much for your attention. Большое спасибо за внимание. Now the coffee break. Again without coffee, but it's fine. So. Вопросы, yes. Ну, пока вот кофе нет, давайте.
So, you replaced process models by neural networks.
Yes.
Is it, does it work, do you assess uncertainty, does it work well in any case? Is it like...
Not in any case. It's a tricky exercise, but sometimes it helps. What I want to say, neural network is approximation. So it's not a process model. If your process model is not running for too long, use process model. You don't need any neural networks to replace it. But if a model run is a long time, then in your optimization loop would run for months, like in case of Milanese. So in this case, it's better to train neural network on a limited set of process model runs. So algorithm is this. So we run a model, say, 20 times. We train very simple data-driven model on this. And then we do optimization with the data-driven model, which is very fast. We find a better solution. Then we run process model again and check if this solution is good or not, because we don't know really. Because neural network says it's good, but process model may say it's not good. So we run process model again 20 times, but not 100 times like neural network. So it takes less time. Then we move in the space of variables, and we every time retrain our neural network. That's a progressive retraining algorithm called MoPrism we use. So that's also Minsker in 2006 with her PhD student did this. So it's a sort of progressive retraining. That's how it is. And then neural network becomes more and more accurate in the proximity, closer and closer to the optimal solution. It's not accurate elsewhere, from very far from, but it's becoming more accurate in where you need it. So that's how it is.
Я тоже еще задам вопрос, если. Ну, дело в том, что где-то у нас в 80-х годах было много таких постановок. Вот. Ну, очевидно, у нас была лаборатория Яшинская, которая занималась задачами. Вот. И, ну, что потом выяснилось? Это, может быть, они не довели это все. Но выяснилось, что когда много переменных, ну, там, сотни, да, у вас, может, даже тысячи перемен. Ну, решение ясно не может быть единственным. Вот, оно очень сильно зависит от критериев оптимизации, которые выбраны, да, там какие-то функционалы придумывают. Да. Вот. И, ну, по крайней мере, на таких физически ясных задачах было понятно, что лучше вот такой перебор simulation, делать simulation из физических соображений. Да. Вы можете эти simulation, конечно, выбрать всю физику, которую вы знаете, вы туда можете толкнуть. Вот. А вот таким формальным методом оптимизации, формальным надо относиться с неким недоверием, с осторожностью. Да. Вот, и это, конечно, ну, вот я до сих пор не знаю, ну, можно... что все-таки лучше. Ну, наверное, у вас есть опыт.
Вот, окей, значит, simulation — это одно симуляция. Когда их несколько, это сценарный подход. То есть мы можем сказать, у нас 5 сценариев, и мы 5 раз модель для разных параметров гоняем. Вот. Это уже начинается оптимизация. То есть когда 5, ну это уже оптимизация. Потому что есть критерии. Мы же выбрать должны один из 5.
Я говорю, выбрать.
Да. Мы же потом в результате одну модель выберем.
Ну, да.
Это оптимизация. Она, конечно, Mickey Mouse Optimization, но... Ну, хорошо. Да. Но в то время компьютеры... Coffee break, да. Все, давайте обсудим во время кофе-брейк, и кофе уже здесь. Все, спасибо большое.